Okay. Okay, so we're going to look at trig identities here. We have our left side is equal to our right side. And what we'll do is we're going to focus on the left side here. And actually, I've written the question wrong. This is a subtraction sign, right?
Yeah.
Okay. So here, it might be easier if we, it's not always said to do it, but it might be easier if we just kind of write this, instead of writing cos and sine, because it can sometimes be tough, I'm just going to say, almost like a little let statement. I'm going to say let C equal cos. I don't know why I put an equal sign there. And let S equal sine. And what that does is it just is a little simpler for factoring. It's something we might be more familiar with. So this would be C squared, and let's just say cos x and sine x. Okay, so C represents cos x, S represents sine x. So this is C to the power 4 minus S to the power 4. Okay. Well, now I can start to see that this might be a bit of a difference of squares. To find a difference of squares, we need to square root both. So here on the right here, I'll do it in blue. The square root of C4 would be C2. The square root of S4 would be S2. So now that we have that, when we do difference of squares, we take these two values, and we make them the first and second term, and then we just have a plus and a subtraction in between. That's how we factor a difference of squares. So now we have C squared plus S squared and C squared minus S squared, okay, is equal to 1. Oh, sorry, I don't have to keep writing that. We're doing a trig identity here. Okay, so we still are working on the left side, and I just changed that for the factoring part. I'm actually going to switch it back now, okay? When I switch it back, this will read cos, and we still have brackets, cos squared x plus sine squared x times cos squared x minus sine squared x, okay? And maybe you could have seen that from up here. I just find sometimes might be easier if it's not written as an identity. So now that we have this, it's not quite what we want, but everything is, at least on the right, they're only working with the sign. So I'm going to use our Pythagorean identity. We have a Pythagorean identity that states cos squared x plus sine squared x equals 1. And I'm going to replace cos in both of these. I'm going to manipulate this. Cos squared x is also equal to 1 minus sine squared x. So we're going to replace the cos with those two values. So replace this and replace this with 1 minus sine squared x. So we'll end up with, I'll write this in red, 1 minus sine squared x plus sine squared x. This is again 1 minus sine squared x minus sine squared x. Okay, we can kind of drop the brackets because it's just addition and there's nothing to really distribute. So we have 1 minus sine squared x plus sine squared x, 1 minus sine squared x minus sine squared x. Okay, farthest to the left here, this negative and positive, they eliminate. They create a 0. So 1 minus 0 is just the value of 1. So we just have 1 left in this bracket. On the right bracket, this is where maybe calling sine x again s might come in a little handy. Think of it like this. I'm going to reapply that let statement, so I'm going to write it in green. So we get minus s squared minus s squared. Okay? Well, think of it like there's actually a 1 here. So it's kind of like negative 1 minus 1. When we do that, you're left with negative 2. Okay, so we have 1. The easiest way may be to write it like this. Negative 1 minus negative 1 is equal to negative 2. So we're just looking at the coefficients in front of the s's. The s squareds are going to stay the exact same. So now I'm going to be left with negative 2s squared. I know I've gone in and out of that statement, but this is essentially sine x. So I'm going to rewrite that sine x now. So we have 1 minus 2 sine squared x, okay? And 1 times that is just whatever that is, right? So 1 minus 2 sine squared x. And if we scroll way up to the top, even though I didn't really stay within my boundaries here, 1 minus 2 sine squared x is exactly what we were looking for. So we've just kind of proven that trig identity there.